Hello and welcome to this lecture on advanced electric drives. In the last lecture, we are discussing about the steady state operation of a synchronous motor. The motor is operating under steady state condition. And what do we mean by steady state condition? By steady state condition, we mean the speed is constant and the currents and the voltages which are applied to the machine are having constant amplitude and phase angle. So, we will start from that steady state operation of synchronous motor in today's lecture. Now, in this case, by steady state we mean the following things. The currents are constant in amplitude and phase angle. The phase angle is also constant. So, we can say here that we are, of course, we are talking in rotor reference frame. The currents are evaluated in the reference frame attached to the rotor, which is rotating at synchronous speed. So, we can say that IDS equal to capital IDS is constant, and similarly we can also say that IQS is equal to capital IQS, that is also constant. So, the currents are constant is phase angle and also in amplitude. These are the stator currents. Now, what about the rotor currents? The field current is also constant. So, we can say here that IF is equal to capital IF, here this is also constant, the field current is also constant and the speed is constant. So, we can say that omega r is equal to omega E, the motor is rotating at synchronous speed in the steady state condition, and that is constant. We know that in synchronous motor we also have the damper windings, and the damper windings are present in the D axis and Q axis respectively. What about the damper winding currents? Here we also assume that the flux linkages in the rotor are constant. It means psi kd and psi kq are constant, there is no transient disturbance, and hence naturally the damper winding currents will be equal to 0. So, we can assume here that I kd is equal to I kq, these are 0, and under this condition we had evaluated the torque in the last lecture, and the torque is the steady state torque of a synchronous machine, and we can express this steady state torque in the following way. Te was given by 3 by 2 into P by 2 into LMD IF IQS plus LDS minus LQS into IDS into IQS. So, this is the torque in terms of inductances. We can also replace this torque in terms of reactances, because we know that the inductance can be obtained by dividing the reactance by the base speed. So, we can also say that is equal to 3 by 2 P by 2 1 by omega b is the base frequency in radian per second, into XMD IF into IQS plus XDS minus XQS into IDS and IQS. Now, this torque expression does not have any damper winding currents, because the damper winding currents are equal to 0, and this expression has got two distinct parts. The first part, this part is called the reaction torque. This is because of the reaction between the field and the stator current or the armature current. This is also called the field torque. It is produced because of the field current. So, we can call this to be the reaction torque. Or field torque. What about the second term? Second term, if we see, this basically an expression which has got xds minus xqs, and this is called the reluctance torque. And this is called the reluctance torque because the torque is a function of xds minus xqs. It means if we have a silent pole machine, in a silent pole machine we have xds different from xqs. In fact, xds is higher than xqs in a silent pole wound field synchronous machine. So we have a torque production, and that torque is given by xds minus xqs into ids into iqs. So this is called the reluctance torque, which only appears in a silent pole machine. In a cylindrical machine, xds is equal to xqs. Since xds is same as xqs, the torque is equal to 0. So these are the two torques which appear in the steady state in a synchronous machine. Now, having derived the torque equation, we would also like to see the equation for the voltage. The voltage equations are as follows. So we can write down the voltage equations. And these are in the rotor reference frame. And since we are talking about the steady state situation, the P terms are equal to 0. The P means, the small p means d by dt. So we can say that the P terms are equal to 0 because we are talking about the steady state operation. In the steady state condition, in the rotor reference frame, the variables are all DC variables, because if we observe the currents of the stator from the rotor reference frame, the currents and the voltages in the steady state condition will appear to be DC variables. And since we are talking about the steady state operation, the P terms are equal to 0. So the equations are further simplified. So we can write down the equation in the d axis VDS. We are writing capital because these are the DC variables. That is equal to Rs into IDS is the resistance drop minus the speed is omega r, and omega r is same as omega e. So we can say it is omega e into the stator flux linkage in the q axis, that is psi qs. And what is psi qs? That is LQs into IQs. We can also rewrite this in terms of reactances. Reactance here, Rs into IDS minus omega e by omega b into XQs into IQs. The equation is very simple, and this is a DC equation. It is an algebraic equation because we are talking about the steady state condition. Similarly, in the q axis, if we write the voltage equation in the q axis, we can say here what is VQs? VQs is equal to Rs into IQs plus the rotor speed into the q axis flux, d axis flux. So here omega e is the rotor speed, and the d axis flux linkage is given by LDS into IDS plus LMD into IF. Damper currents are not are 0, they are not existing. So we have the d axis flux linkage is given by LDS into IDS plus LMD into IF, because IKD is equal to 0 because we are talking about the steady state condition. Now this can be written in terms of reactances also. So we can, that is equal to Rs IQs plus omega e by omega b into XDS IDS plus XMD into IF. Now from these two voltage equation, we can draw the Phasor diagram. So we can draw the Phasor diagram with an intention to find out the relationships between the Phasor relationships between the voltage and the current. So we can draw a Phasor diagram. So to draw the Phasor diagram, we have to represent all the variables in terms of phasors. So let us say this is our d axis. So, this is our d axis, because we are talking about a solid pole synchronous machine. We have distinct d axis and q axis. So, this is our d axis and this is our q axis. And the d axis will have the field winding. So, we can show that in terms of the field pole, and the field current is along the d axis. So, we can say this to be If. So, we can see that we have two components in this case, a d axis component of voltage and q axis component of voltage, VDS and VQS, and we can write these two equations in the d axis and q axis respectively. So, in the q axis we can show this term. So, for example, if you show this term here, this is basically the q axis equation, and we are representing all the variables in the q axis. So, this xmd into If or lmd into If into omega e represents the field induced EMF. So, we can say that is equal to Ef. And what is Ef? Ef is same as omega e into lmd into If. So, this is this term, and then we also have a term which is omega e into LDS into IDS, that is also in the q axis. So, we can show that term here, that is this term is omega e into LDS into IDS. And what about this currents IDS and IQS? The stator current will be along any arbitrary direction. This is the armature current IS, and this IS can be resolved into two components along the two axes d and q respectively. So, if we resolve this along d axis, this would be IDS, and if we resolve the same current along the q axis, we get IQS. So, we can resolve this along the q axis here and we get IQS. And this omega e into LDS into IDS is basically the component of this current along the d axis, that is IDS. Similarly, apart from the resistance part, we have already accounted for this part and this part. This resistance part we can add little later. So, let us come to the q axis. So, in the q axis, d axis, we have this term. In the d axis, what we have here is minus of omega e LQS into IQS. Now, the d axis here is vertically downwards. This is our d axis. Minus of omega e into LQS IQS is opposite to d axis. So, we can show that this is our d axis, that is minus omega e LQS into IQS. So, this is again an induced EMF which is shown as a phasor. Then we can add the resistance drops. Now, the resistance drops are Rs into IQS, which will be in the q axis, and then Rs into IDS, which will be in the d axis. And the resultant voltage would be somewhere here. So, this is V D Q S, this is also a phasor. So, we have been able to write the equation in the d axis and the q axis. We had two algebraic equations and we separated these two equations and we added the phasor in the q axis, in the d axis, and we could draw the final space vector or the phasor of the voltage V D Q S. The V D Q S is a phasor of the voltage applied to the stator of the synchronous motor. Now, here we can also define a value called gamma. Gamma is the angle between the current phasor and the q axis. So, this is our angle gamma, this angle is gamma. So, we can very well say here that what is IDS? IDS is equal to IS into sin gamma and IQS is equal to IS into cos gamma. So, we can write down the components of the stator currents IDS and IQS in terms of IS and gamma. Gamma is the angle between the stator current phasor IS and the q axis which we have shown here. Now, the purpose of this analysis is that we can find out the power factor here. The power factor is the angle between applied voltage phasor and the current phasor. So, this is the power factor angle. So, we can say that this angle between the V dqs and IS, and this is equal to theta. Theta is the power factor angle. So, this is the phasor diagram of the synchronous motor operating under steady state condition, and we have deliberately taken a silent pole synchronous machine to show that voltage phasor to get the resultant voltage phasor applied to the synchronous motor. Now, from this we can also find out the torque. So, we have already seen the expression for the torque. Now, if we just rewrite the torque expression, so we will obtain here Te is equal to 3 by 2 into P by 2 into LMD IF IQS plus LDS minus LQS into IDS into IQS. And we have already seen that the first part is called the reaction torque or the field torque, and the second part is called the reluctance torque. Now, if we express this in terms of, let us say, IS only, we can also say that is equal to 3 by 2 into P by 2 LMD IF. What is IQS? IQS is given as IS into cos gamma, that we have already seen what is gamma here. IQS is IS into cos gamma. Gamma is the angle between IS and q axis. So, that we have already seen there, and that is why we have written LMD into IF into IS into cos gamma plus LDS minus LQS, and if we replace this IDS and IQS by IS sin gamma and IS cos gamma respectively, so we get here IS square sin gamma and cos gamma. So, this is the equation that we have. This equation is the equation of the torque equation of a synchronous machine under steady state condition, but this is also a little complex because this involves IS square, it is a nonlinear equation. So, if we want to have a simplified torque expression from the point of view of ease of control, we would like to take some condition here, and the condition is gamma equal to 0. Now, if you put gamma equal to 0, what happens here? Gamma, the angle between IS and IQ, I mean the q axis is equal to 0, we will see that cos gamma is equal to 1 and sin gamma equal to 0. So, we can see that Te is equal to 3 by 2 into P by 2 into LMD into IF into IS, and the second term vanishes, this term becomes equal to 0. The second term does not exist and we have only the first term, and in the first term what we can do here is that we can keep IF constant and we can change IS. IS is the stator current. So, we can keep the field current constant and vary the stator current and control a synchronous machine just like a DC machine, and this condition is called the vector control of synchronous machine. So, we can say that this is called the vector control of synchronous machine. Of synchronous motor. So, if gamma equal to 0, what are the two components of currents? We know that IDS is equal to IS into sin gamma, that becomes equal to 0. So, if gamma equal to 0, IDS vanishes. What about IQS? IQS is equal to IS into cos gamma, that is equal to IS, same as the stator current. So, in case of a vector controlled synchronous motor, IDS does not exist, IDS equal to 0, and the torque is controlled by controlling IQS. And if we want to have very high dynamic response, we can keep the field current constant and control the torque by controlling the stator current or the armature current. So, this is what we have here. And what about if gamma is not equal to 0? That is not vector control, and we call that to be the angle control. So, we can say that angle control gamma is not 0. If we operate the motor under any other condition for which gamma is non-zero, that is called angle control of synchronous motor, because for that the dynamics is not as fast as what we have in case of a vector control drive. Now, we will see that how the dynamics improves in a vector control drive when we have gamma equal to 0. Now, before that we will take up some implementation issues. Now, if we make gamma equal to 0, how can we implement vector controlled synchronous motor drive system? Now, we will see that how to implement implementation of vector controlled synchronous motor drive. Now, here gamma is equal to 0. So, we are saying that gamma equal to 0, which means IDS is equal to 0, and we can keep IF constant and IQS is variable. We can have two approaches. One approach is that implement the drive using a current source inverter. So, if we use a current source inverter, you can inject the current in such a way that IDS becomes equal to 0 and IQS can be controlled by changing the DC link current. So, the first implementation is CSI fed synchronous motor. So, here what we have in this case is the following, that we have a force commutated CSI. This is the schematic block diagram. This is our CSI, and we have a DC link here, and we have a large inductor in the DC link to keep the current constant, and the CSI feeds the synchronous motor. And we have the field winding here, and the field winding is fed through the slip ring, and we can keep IF constant. This is the field winding, and we have to also control. We have the 3-phase AC in this case, and this is a converter, a 3-phase converter. We have 3-phase AC input, and here we have a phase regulator. To control the synchronous motor, we have to use a position sensor. That is very much necessary, because the motor is being operated with self control mode. Unless we have a position feedback, we cannot have self control mode. So, we have to have a measurement of theta r. So, this is achieved by using an encoder. So, we can use an encoder here to obtain the position information, that is theta r. And here, as we already discussed, that we can we can make gamma reference, gamma star means gamma reference equal to 0. We are talking about the vector control drive. So, we can make gamma, this angle between IQS and IS phasor equal to 0. And then what we have, we can have a current feedback here. So, we have a current regulator. And we will give a torque command, and the torque command is same as IQS command, because here IQS is variable. So, we can give a reference IQS. If we change IQS, the torque will automatically change. So, this IQS is same as IS. So, we can give the command for the stator current through the current regulator, and the current regulator will have a feedback of the DC link current. So, we can have a current sensor here, and this I let us say that this inverter input current is being sensed here by means of a current sensor. So, we have a current sensor here, and then the triggering signal is generated, and the converter is controlled so as to achieve the current regulation. So, in the steady state condition, II, the inverter currents will be such that the required current magnitude is injected into the stator of the synchronous machine. Now, when we go for this current regulation, we know that in case of a CSI, this CSI is a auto sequentially commutated CSI. So, we call this to be auto sequentially commutated CSI. So, here what we have in this case is that there is a phenomena called overlap. When we have more and more current, the output current is not exactly a quasi square wave. In ideal condition, what we have here is this, that the output current should be a quasi square wave like this, and this duration is 120 degree, and we have a symmetrical condition in the positive half and in the negative half. But however, when the current increases, there is a progressive delay in the overlap. So, we call that to be an overlap delay, and because of that the current actually lags little bit by some angle. So, the actual current becomes something like this. It takes some time to rise, takes some time to fall here. Similarly, it takes some time to rise in the opposite direction, falls like this. So, effectively the current is delayed. So, to compensate for the overlap delay, we have to give some compensation here. So, here what we have is that we have the commutation delay here, commutation delay compensation. So, this is obtained, this is basically a function of II, and this is given to the phase regulator. So, this delay is because of the commutation progresses, and there is a delay of the current. As we increase the current magnitude, the commutation delay also increases, and to compensate for that, we have to have a compensator, so that we advance this angle in such a way the delay is cancelled. So, this is actually overall schematic diagram of vector controlled synchronous motor drive, which is fed from a CSI. Now, there is an other way of implementing the same vector control drive, that is by using a current regulated pulse width modulated VSI. So, we will see how we can implement a vector control synchronous motor drive using CRPWM inverter drive. So, we will see that implementation of vector controlled synchronous motor drive with a current regulated voltage source inverter. Now, this drive is popular for medium power application, not for very high power application, because this involves a PWM voltage source inverter, and here the PWM frequency is expected to be in the range of few kilohertz to achieve good current regulation. So, this drive is suitable for low to medium power application up to a few hundreds of kilowatt, not in the megawatt range. So, what we have here, we have a CR PWM VSI. So, this is the VSI we have, and this feeds the stator of the synchronous motor. And similarly, we have the field in this case, and field is separately excited. We have the slip rings in this case. So, we can have the field current here, we have a separately excited field winding here, and then we will have the encoder for the position feedback, and this VSI is supplied from a rectifier, an uncontrolled rectifier bridge. It could be a 3-phase bridge. So, we have 3-phase AC input, and then we have small filter here, small inductor and capacitor to filter out the ripples in the rectifier output, and what we feed to the current regulated PWM VSI are the 3 reference currents, IA star, IB star and IC star, and these are basically the actual currents here, IA, IB and IC. The inverter injects this IA, IB, IC in such a way that they are close to IA star, IB star, IC star. So, this adopts the hysteresis current control to control the 3 currents of the 3 phases A, B, C in such a way that the currents follow their reference value very closely. So, this IA star, IB star and IC star are obtained by means of a transformation, and the transformation is basically by the rotor angle. So, what we have here is the rotor angle, which is obtained from the encoder. So, we can call that to be the theta, and this rotor angle transforms this VDS and VQS into IA, IB and IC. So, what we have here, we have the 2 commands in this case, and the commands are the torque command, and this is IQS star, and we have the flux command, IDS star, but this IDS star is made equal to 0. So, what we give here, we have IDS and IQS, and we make deliberately IDS equal to 0 to achieve vector control, because gamma equal to 0 is same as IDS equal to 0, and we apply here IQS, and this block is the transformation block. So, we transform this IDS and IQS from the rotor reference frame to the actual stationary reference frame, and this IA, IB, IC are the currents in the stationary reference frame, which become the reference currents for the CR PWM VSI, and the VSI injects this current to the stator phases of the synchronous motor. So, as we have already seen that we can also implement the vector control of synchronous motor drive from a current regulated PWM voltage source inverter, and this is suitable for low and medium power application up to a few hundreds of kilowatt, not in the megawatt range, because this involves a PWM VSI which has got the power limitation. And what we have here is that we are able to transform, in this case we have a transformation here, and we transform IDS and IQS into IA, IB and IC, and this IA, IB and IC are the reference currents for the CR PWM VSI. Now, what is this transformation? This transformation we have already discussed in the previous lecture. Just to recapitulate that once more, we can we can write down the transformation once again. So, what we have to obtain is IA star, IB star and IC star, and we obtain that by a transformation involving theta r, and we have cos theta r1 and cos theta r2 minus of sin theta r minus sin theta r1 minus sin theta r2, and here we have IDS star, the reference value of IDS current, and we have IQS star is the reference value of Q axis stator current, and theta r1 is equal to theta r minus of 2 pi by 3 and theta r2 is equal to theta r plus 2 pi by 3. So, this transformation transforms IDS and IQS into IA, IB, IC, which are used for the reference for the CRPWM VSI. Now, this actually is the aspect of implementation. The question that we asked little earlier, that how are we guaranteeing that in vector controlled synchronous motor drive the response is quite fast. Now, to be able to understand that, we have to derive the equation for the torque of the synchronous motor. Now, this also we have already done in the past. We will just recapitulate the torque equation that we have derived in the earlier few lectures of this particular course. So, response or the dynamics of synchronous motor under vector control, which means gamma equal to 0. Now, we are always talking about, or we are always trying to model the synchronous machine in the rotor reference frame. It means our reference frame D and Q axis are housed on the rotor. So, we can write down the equivalent circuit in the D axis and the Q axis respectively. So, in the D axis what we have the resistance, we have the back EMF, we have the leakage inductance of the stator, we have the magnetizing inductance of the stator, then we have the leakage of the damper winding, the resistance of the damper winding, and then we have the leakage of the field winding, the resistance of the field winding, and then we have the voltage of the field winding. So, this is VDS, and similarly we can also write down the Q axis equivalent circuit, the resistance, the back EMF, the leakage inductance in the Q axis stator, the magnetizing inductance in the Q axis, and then we have the leakage of the damper winding, then we have resistance of the damper winding. So, this is the Q axis voltage VQS. In the D axis equivalent circuit, we can define the various parameters and also the variables. So, we have the stator resistance is RS, the leakage of the stator is LLS, the field leakage inductance is LLF, the field resistance is RF, damper leakage inductance is LLKD, and the damper resistance is RKD. All the variables are referred from the primary side. And then we have the magnetizing inductance, which is LMD here, and this is the field voltage VF. The field current is IF. This is the damper current is IKD. The stator current here is IDS, and this is the back EMF what we have here with this polarity, and this is omega E into psi QS. Similarly, here in the Q axis we have the stator resistance RS, this is IQS is the stator Q axis current, LLS is the stator leakage inductance, then we have LMQ is the magnetizing inductance in the q axis, LLKD is LLKQ. The leakage inductance of the damper in the q axis, and this is our q axis damper current IKQ, and this is RKQ, the resistance of the damper. All the parameters are referred from the primary side. Now here we can derive the expression for the torque. The torque expression, this is our psi ds, the flux linkage in the stator d axis, and this back EMF in the q axis would be this plus and this minus, and this is omega e into psi ds, and this flux linkage is psi qs, the flux linkage in the q axis stator, which is the flux linkage associated with the magnetizing inductance of the q axis and the leakage inductance of the q axis. So we can write down the expression for the torque. Te is equal to 3 by 2 p by 2 into psi ds IQS minus psi qs into IDS, and if we simplify this, we will get the following expression. Te is equal to 3 by 2 into p by 2 into LMD IF plus IKD into IQS minus LMQ IKQ into IDS plus LDS minus LQS into IDS into IQS. So this is the expression for the torque involving all variables. So this is the exact expression for the torque, both are under the steady state condition and the transient condition. Here we are trying to understand the dynamics of the vector control synchronous motor drive. So we have to take into account the transient condition as well. We are not only talking about the steady state condition, we are talking about the steady state as well as the transient condition. So here all currents will be existing. We have the currents of the field winding, currents of the damper winding in the d axis, damper winding in the q axis, we have IDS and IQS. Now in vector control drive we put gamma equal to 0. So we can say that for vector control, gamma is equal to 0, and it also means IDS is equal to 0. So if you put IDS equal to 0 in this equation, what happens? So this quantity will vanish. We have an IDS here, and this IDS will be 0, and similarly here also this quantity will also be 0. So we can write down the expression for the torque. Te is equal to 3 by 2 into p by 2 into LMD IF plus IKD into IQS. This expression is simpler than the complete torque equation, but yet it involves IKD. IKD is there. So IKD is the damper d axis current. Now what is the value of IKD? Now to be able to find out the value of IKD, we have to write down the equation for the d axis damper circuit. Now if we see that, so we keep here IF constant. IF is not changing, that is equal to capital IF. And what about psi KD? Psi KD is equal to LKD into IKD plus LMD into IF plus IDS. But here under the condition that we are operating with vector control, IDS is 0. So this quantity does not exist. So this is equal to 0. So what we have here is the following, and IF is constant. So we can replace that IF by capital IF, which is a constant quantity, and we can write down the equation for the damper. The damper winding is VKD, and the damper winding is a short circuited winding. There is no voltage applied in the damper winding. So VKD is equal to 0. It is a shorted winding. That is equal to RKD IKD plus P psi KD. And what is this psi KD? Psi KD is LKD IKD plus LMD into IF. IF is constant. So the derivative of a constant quantity is equal to 0. So, the small p here, this is a small p signifies d by dt, the derivative operator. So, that is equal to RKd into IKd plus LKd into PIKd. Now, since we do not have any applied voltage, this current IKd will be 0 for steady state condition. Even in the transient condition, if we do not change IF, this current will be equal to 0. So, it means, which implies IKd is equal to 0. So, we have the equation for the torque, TE is equal to 3 by 2 P by 2 LMD IF plus IKd into IQS. So, we can write here that this is equal to 3 by 2 into P by 2 into LMD into IF into IQS. So, IKd is equal to 0, IKd does not exist because the field current is constant. So, since we are keeping the field current constant, IKd is equal to 0. So, this is actually the equation of the torque, and it says that if we keep IF constant, torque is proportional to IQS. So, this equation is a simple equation in the sense that IF is kept constant. So, we can keep IF constant and we can change IF, we can change IQS to change the torque, and if we change IQS, torque will be changed proportionately. So, we can show it in terms of a block diagram. So, we will have in this case the field current IF, and we have IQS, and this is multiplied with 3 by 2 into P by 2 into LMD, and what we obtain is the torque. So, there is no dynamics involved here. We can keep IF constant and we can change IQS to control the torque. So, if we show it in terms of a response, so this is our control response. So, we can change here, we can keep IF constant, IF is kept constant, T is in the x axis, and if we change IQS in a step, the torque will also change instantaneously. This is IQS and this is the torque. And that is why the vector control drive has got very good dynamic response. One of the advantages of using vector control drive is that the dynamic response is very fast. The torque changes immediately when we change IQS because the field current is kept constant, just like a DC machine. However, just to have a small remark here, in vector control drive, although we have very good torque response, there is a little bit of difficulty. The difficulty is that it leads to lagging power factor. The vector control drive in synchronous motor, in which we keep IDS equal to 0 and control the torque by controlling IQS, results in a lagging power factor that we can see in the corresponding phasor diagram. So, what we have here is that IDS equal to 0. So, when we have IDS equal to 0, this is the D axis and this is the Q axis, and we have the field current which is constant. So, we can show this is the field current IF and this is a field induced EMF, we can say that is EF, and IDS is equal to 0, but IQS is finite. IQS exists. So, if we, for simplicity, if we ignore the resistance drop, the reactance can be added here. And what about the current? The current is along the Q axis. So, this is our IS, gamma equal to 0 here. So, the current is along the q axis. So, we do not have any component of Is along the d axis, and if we add this reactance here J Is into Xs, and we can assume that there is no resistance drop. So, if you ignore the resistance drop J Is Xs, Is is along the q axis, and J is, say for example, we are, for simplicity we are talking about cylindrical synchronous machine where the synchronous reactance is constant, Xs is constant here. So, this is our Phasor diagram, and this is the voltage in this case. So, this voltage Vf and If, and this is our current in this case. So, this is the power factor angle, that is theta. The current lags behind the applied voltage, and hence in a vector control synchronous motor drive the power factor is lagging. However, the torque response is quite fast. If we want to have torque change, we can change IQS and the torque changes instantaneously. Now, we can have one relaxation. If is not constant. So, if we have the same vector control drive with If variable, let us see what happens. Dynamics of vector control synchronous motor drive, where If is not constant with variable field operation. So, what we have here is that gamma is equal to 0 and IDS also is equal to 0, but If is not constant. So, if If is not constant, we cannot ignore IKD. We understand that VKD is equal to 0 is equal to RKD IKD plus P psi KD. What is psi KD? Psi KD is equal to LKD IKD plus LMD into IF. IF is not constant. So, we can rewrite this equation in the following fashion: 0 is equal to RKD IKD plus P LKD IKD plus LMD into IF. Now, this will lead to a finite value of IKD. IKD will not be equal to 0 here. Now, if we find out the expression for IKD, what is IKD here? IKD is equal to minus LMD P IF divided by RKD plus LKD P. So, this is what we have in this case. So, IKD is finite, IKD is not equal to 0. So, if IKD is not equal to 0, the torque will not be instantaneously variable when we vary IQS. Now, let us see the expression for the torque. Now, if you see the expression for the torque expression was for vector control drive, TE is equal to 3 by 2 into P by 2 into LMD into IF plus IKD into IQS. Now, IKD is not 0 because we are changing also IF. So, when we are changing IF, IKD does exist, and because of that the torque equation becomes little more complicated compared to the situation where IF was constant, the field current was constant. Now, here we can draw a block diagram to illustrate how the torque changes with a change of field current. So, what we have here is the following. We have the field current here, and the field current is not constant, and that changes with this transfer function LMD P by RKD plus LKD P, and this is IKD, and IKD is added with IF, and then we have a multiplier, and this is multiplied with IQS, and we have 3 by 2 P by 2 into LMD, and this is the torque of the synchronous motor. So, we see that when we change IF, there will be a finite IKD, and the IKD will try to delay the torque response. It will try to delay it because we have a negative term here. The effective current that is produced here, this is IF plus IKD, this will be less than IF, and finally in the steady state condition IKD will be equal to 0, but in the transient condition when we are changing IF to change the torque of the synchronous motor, the effective current here IF plus IKD will be less than IF because IKD is negative to keep the flux constant, and hence the torque will be delayed. So, in the next lecture we will see how the torque response changes when we go for angle control. It means gamma is not equal to 0. Gamma is not equal to 0 means we have both IDS and IQS, and the torque equation becomes more complex, and that we will be seeing in the next lecture.